Hi, it's Kate, and this is the third video for week 7 of Math 23. Now we're going to talk about another type of continuity. It's called uniform continuity, and it's really important that, obviously, to master the limit definition of continuity that Ross is using with these sequences, the good sequences, the bad sequences. But one of the things that you really need to know up, down, left, right, all over the place is the epsilon delta definition of continuity, because the epsilon delta definition of uniform continuity is the only one that really exists. So what's the difference between uniform continuity and just regular run-of-the-mill continuity? Well, it's really all a matter of the order of quantifiers. So for continuity, we talk about a function being continuous at a particular point. And when we talk about the delta that matches to the epsilon, that delta is specific to that point that we are saying is continuous on this function. So for continuity, y is agreed upon before the epsilon delta game is played. We say, here's a point. How can I get within epsilon of that point's function value? And you say, oh, well, okay, at that particular point in the function behaves like this. And so if you're within delta of that input value y, then you'll be within epsilon of the function outputs. Now for uniform continuity, we do not specify a point. We just say epsilon in general. And you're absolutely right if you're already thinking this. That means that no matter where you are on the entire interval, we want to land within epsilon of the function value of a point on that interval. And so the only thing that's specified in advance for uniform continuity is epsilon. And delta is chosen that meets the challenge. And it doesn't matter which point you're talking about in the interval. This epsilon delta partnership works for every single point on the interval. So that's sort of what we mean by uniformly continuous. Epsilon delta partnership works everywhere along the interval. That whenever you're within delta of the inputs, then you'll be within epsilon with the outputs. So let's take a look here. For a function f whose domain is a set S, continuity, very vanilla definition of continuity, means for all y in S, that means you could zoom in at any point in S. For all epsilon greater than 0, there exists a delta. Note that the fact that we have listed y first, which means that this choice of delta is very y specific. This means at any point that is pre-chosen, whatever the epsilon is, there's going to be a delta such that if you're within delta of that particular y, then your function values will be within epsilon of each other. And this delta is y specific. Now uniform continuity, however, means that, note that we do not say for all y that are in the set S. We're just saying in general, for all epsilon greater than 0, there exists a delta greater than 0 such that for all inputs on this set S in the domain, if the inputs are within delta of each other, then the outputs will be within epsilon of each other. Make sure that that is clear in your mind what the difference is there. Here with continuity, when we say for all y in S, this happens, that means that this delta could be changing depending on which y you're at. Whereas for uniform continuity, we do not specify a y. We say for all epsilon greater than 0, there exists a delta greater than 0 such that if two inputs are within delta of each other, we don't specify where they have to be on that interval. Just as long as they're within delta of each other, then their outputs, their function values, will be within epsilon of each other. Now let's take a look on things that are maybe continuous but not uniformly so. First here on the interval from 0 to infinity, and I do want to adjust this slight typo because we never should be using a closed bracket on that, and depending on when you've printed out your notes for the week, perhaps you're looking at the not up-to-date ones because I'll be changing this as soon as I'm finished with this video. But on the interval from 0 to infinity, note that it is not a bounded set. The squaring function is continuous but not uniformly continuous. Why is that? Well, when we look at the same delta range on the squaring function, when we're looking at a very small change in input values, at first, at the beginning of the interval, that corresponds to a very small change in output values, right? Note that this very small change in input values corresponds to a very small change in output values, but that same change in input values moved over here further down the interval corresponds to an extremely large change in output values. And of course, as we're looking at this entire interval, that same change in input values corresponds to larger and larger and larger and larger change in output values. So there is no one epsilon delta partnership that ever works, because as you keep going closer and closer further down as you make those input values approach infinity, the same delta tolerance does not match up to the same epsilon tolerance, because it maps to a larger and larger and larger interval of output values for the function. Let's take a look on 0 to 1, which is not closed. The function that is 1 over x is continuous but not uniformly continuous. Sort of the same issue that's happening here. The same problem here is my 1 over x on the open interval from 0 to 1. The same problem is essentially happening. The set itself, we have this asymptote here at x equals 0, and that's causing a problem because these epsilon delta partnerships are breaking down the closer and closer that we get to 0. Because what is a nice input range over here, what provides us with quite a small range in output values over here, this is our interval in the domain, maps to a very brief interval in the image, gets larger and larger and larger as this interval slides in this direction. It's the same width over here, but it explodes in terms of the size of the interval of function values in the image that it corresponds to. So that's where uniform continuity is breaking down over here. What's interesting is that on a closed bounded interval, you might have already seen us setting up for this, but on a closed bounded interval from A to B, continuity implies uniform continuity. Here we had two functions which were continuous but not uniformly so. One was defined on an unbounded set, one was defined on a not closed set. But if we do have a continuous function that is defined on a closed and bounded interval, then continuity implies uniform continuity. And the proof uses the Bolzano-Weierstrass theorem, which is a proof that we'll be looking at this week. Here are some other things. By definition, if a function is continuous at a particular point, and we have a sequence that converges to that point, then the function values, converge to the function values of the sequence converge to the function value of the limit. If the sequence itself is merely Cauchy, we know it converges, but we do not know what it converges to. And so to guarantee that the function values of the sequence are also create a Cauchy sequence, we must require that the function itself be uniformly continuous. These are things, again, we'll be exploring this week. Here's another interesting point, that if we have an open interval and a function defined on an open interval, it can be continuous without being uniformly continuous. We've seen that already a bit, but note that if we can extend the function f to a function f bar, that's what we're going to call it, defined so that f bar is continuous at these endpoints that are not originally included in the open interval on which the function is defined, then f bar is uniformly continuous on the closed interval from a to b, and f is uniformly continuous on the open interval from a to b. And the most familiar example here is sine x over x, which probably in your univariate calculus class, you found the limit of sine x over x as x approaches 0 being equal to 1. And what's interesting is that on the interval from 0 to infinity, we can extend f to f bar. It has the exact same function values as f everywhere, but since f is undefined at 0, we just define f bar to be 1 at 0. And so what has happened now is that f bar is uniformly continuous on the closed interval, f is uniformly continuous on the open interval, and that's extremely interesting. An interesting result. What we've done is we've taken something that was not clear whether it was uniformly continuous and shown that it was by using this extension method. You might be thinking, hey, wait, I thought that it had to be a bounded interval. I thought it had to be a closed interval in order for something to be uniformly continuous. That is not true. Remember that if we have a continuous function on a closed and bounded interval, then it's going to be uniformly continuous. But that doesn't mean that uniform continuity necessarily needs these things to happen. And this is one great example of how we can take something that we know is continuous but are unsure whether it's uniformly continuous. But if you're able to extend the function to make it continuous on a closed interval, then the original function, which is defined on an open interval, can also be uniformly continuous, as you've shown. Here is f bar, the extension. It is continuous on a closed interval, therefore it is also uniformly continuous. So f itself, since it only differs from f bar at very singular points, it's also going to be uniformly continuous on its open interval. Some alternative criterion for uniform continuity which are sufficient but not necessary is that f is differentiable on the open interval here from a to b, and f prime, the first derivative, is bounded on this open interval from a to b. Uniform continuity, very useful, and will get more and more useful as we finish up this module and move into the third module of this